Hello everybody. In this lesson we're going to review hybridization, which is a concept you learned about in honors chemistry, but we're going to add a little bit about how they know hybridization occurs, what the evidence is for this idea. If you recall, hybridization is when you're combining two or more orbitals of similar energy within the atom into brand new shapes and types of orbitals that will result in equal energy. The analogy that gets used for hybridization is something if you take a poodle and you cross it with a lab, what do you end up with? You end up with labradoodle puppies. So we're combining two different things into something new that exhibits a little bit of the characteristics of both, but they're really their own new type of thing, right? Their new type of dog, new type of orbital. The simplest type of hybridization is what's called sp hybridization. The letters that come in front here, sp, are telling you which orbitals have been merged. Now, we're not smushing them into one new superorbital. What we're doing is we're going to start with two orbitals. They're going to end up still as two orbitals, but they will have different shapes. Their shape will be somewhere in between an s orbital and a p orbital. When you hybridize, these orbitals are now identical, aren't they? We started with two very different size, very different shape orbitals. Now we have two orbitals that are the same. When those two orbitals overlap to share electrons to make a bond, we end up seeing some of the Vesper shapes that we're familiar with, like a linear structure here, 180-degree bond angle. Hybridization helps us see and understand why we're getting the bond angles we do. If an s and p orbital overlapped, you wouldn't get the angle and bond length that you would see in real life. Let's go through each of the types. You'll often see them represented with orbital diagrams, either a classic orbital diagram with lines, or you may sometimes see them with shapes like you see down below. I'm going to highlight the areas we're interested in because it can be hard to see what's really happening. If you look, we're going to take an s and p orbital and hybridize them. Those two right there. We want those to overlap and bond. Those two right there. We started with two orbitals in my yellow box and two out here. We had four orbitals altogether. If you look over here, we have two hybrid orbitals and two that were left alone. So we still have a total of four, don't we? I took two and hybridized them into two new shapes, and I left two of my p orbitals by themselves. And now those two that hybridized have the same energy, don't they? And the two that were left alone have the same energy they had originally. And there's other types of hybrid orbitals. We could have sp2, where we take an s orbital and two of the p orbitals, and we hybridize those. 3 are going to hybridize into 3 new shapes here. 1 gets left alone. I'm not changing the number of orbitals I have. I'm changing the shapes and the energies of the orbitals that I have. And those 3 hybrids will have the same energy, and my p orbital that got left alone that is unhybridized stays at the same energy it was before. sp2 tells me I had an s orbital and 2 p orbitals. This can now make 3 bonds. You have 3 things attached to your center atom, can make 3 bonds with these 3 hybrid orbitals. sp3, we're going to start with 4 and end with 4, but they have different shapes. And if you look, now there's no unhybridized. And all of my orbitals are now at the same energy level. I now have 4 new shaped orbitals that are available to overlap and bond. I can make 4 bonds now, can't I, that will have the same energy and the same length. Right? New shapes here, new energy here. So the new part of this lesson is thinking about how do they know this is occurring. So let's think about a simple molecule. Let's think about CH4. We're going to look at their electron configurations and think about what the electrons need to be doing to make these 4 bonds. We have a carbon with 4 single bonded hydrogens. If you look at carbon's configuration, you have 1s2, 2s2, 2p2. Can you see a problem with the normal state for carbon if it needs to be making 4 equal bonds to 4 separate hydrogens? How many unpaired electrons are there that are available? Right? They need to be unpaired, right? Well, I only have 2. But how many bonds do I need to be making? I need to be making 4 bonds. So they realized there's a mismatch here. Those 2 are not enough. We somehow need 4 unpaired electrons available to bond. So how is carbon going to fix this problem? Well, their first guess was maybe they take this 2s electron and it somehow gets boosted up to the other energy level. Now I would have 4 unpaired electrons, which seems pretty good. But there's a problem here as well. If we have our 4 hydrogens up top and we have our boosted carbon down here, can you see that there is an issue with not all the bonds being formed being identical? You have a 1s and a 2s, and then you have 1s's and 2 p's. These 3 would be the same, but this one here, something's wrong. This is not going to represent what we see in real life. We see 4 equal bonds. Here we have 3 equal bonds and 1 mismatch. This would result in 3 of the bonds being the same and that 4th one not matching. And that is not what we see. It would be a slightly lower energy. It would have a different bond length, and that's not reality. In reality, all 4 bonds have the same energy and the same length. That's how they knew this promotion idea of promoting or boosting an electron up didn't work. The new theory was hybridization. Combining those orbitals to make new shapes that are identical, that have the same energy, same length, that was the new idea. Now, the result of that we see in all sorts of our different shapes, right? We end up with correct angles, correct lengths, correct energies. They end up with a little bit more energy than the 2s, but a little bit less than the 2p. Matches up with all those Vesper shapes you learned about. However, there is one complicating factor in the last few years. They no longer think that d orbitals hybridize like they used to. Now, the Vesper chart, we left it on because a lot of older questions still have it. I'm always afraid that, like, oh, what if you come across one we missed? What if in 10 years they decide, oh, just kidding, it actually does? Who knows, okay? The more accurate they think, more updated theory is called molecular orbital theory. It's pretty complicated. It's not something we're going to really get into. I do have an optional lecture on the website if you are interested. I'm not going to lie. I purposely tried to black it out from my brain. It is not something I enjoy. It's there if you're interested in it. Not something we cover at this level. It's a little bit too hard. You'll get into it at college. All right. So hopefully it was a refresher on hybridization. Hopefully those pictures jogged your memory. Hopefully you remember now what it is you're memorizing on the Vesper chart when it says sp3. And then now you have an understanding of why they think hybridization is a better theory. And you have a sneak peek at something you'll learn in college, which is molecular orbital theory one step further. All right, everybody, that is it. I hope that was helpful. Bye.